Streaming. This is gonna be my last Advent of Code stream, I think. This is day 11. Tomorrow I'm out of town, so I won't be able to stream it. Hopefully I'll get to do it later. And code will be on GitHub. What else is there to say? Uh, I've been posting these VODs to YouTube as well. Not that anybody cares. Code also ends up in GitHub. Um, I don't know. Not much to say. I hope it's easy tonight. I hope yesterday was the hardest. But who knows? Who knows? Who knows? I mean, there's no guarantee even that day 12 will be easy. Even normally the last day is easy, but that's because I used to be Christmas Day. I don't know. I don't know what's happening. I want to go to sleep so that I can be well rested for my flight tomorrow. We'll see. We'll see. We'll see. It has been a fun year though. I like how straightforward everything's been so far. There's been nothing too obtuse or strange or anything. Okay, this is like a graph problem. One of the else notices you mentioned, it's a good thing you're here. We just saw a new server rack. We don't have any luck getting the reactor to communicate with it. You glance over the room and see a tangle of cables running from the server rack to the reactor. She rushes off, returning early with a list of devices and their outputs. Devices, outputs. Yep, it's a graph of some sort. These are edges. Those are pretty sure that the issue isn't due to any specific device, but rather that the issue is triggered by a data flow from some specific path through the devices. Data only ever flows from a device through its outputs. It can't flow backwards. Right. So it's a directed graph. After dividing up the work, Els would like you to focus on devices starting with the one next to you. There's one called U. Wait. Oh yeah, there's one called U. Ending with the output reactor labeled out. You need to find every path from U to out. Oh, I just looked at this recently. In a directed acyclic graph, uh, it's based on the number of edges, but you basically just count. You start, and then you count, and you label how many ways to each path from where you started. You do need to topologically sort. Right. You have to topo sort so that you don't ever miss. Uh, I remember how to topo sort though. I'm not sure I remember how to topo sort. Okay. How do you topo sort? Let's go ahead and read it. But this is paths through the directed acyclic graph. First you topo sort, and then you run through the nodes in topo sort order, and you just add for each edge going out, you just add the number of paths from your current node to it, and then you look at the output. How do you topo sort? What do I not remember? Um, so let's split by this source targets stir, and then edges. So it's a default dict which is in the collections. And it's going to a set for target and targets dot split on spaces. Right, so that's our graph. How do we sort them? You just got to make sure everything comes before everything after it. How to topo sort? I used to know how to topo sort. Why do I not know? Oh, look. Oh no, wait. That's fine. I guess some things probably just terminate randomly, which means there's no sort. Which is fine. Okay, I use defaulting. It's fine. How to topological sort. Oh my god. Uh, use Kahn's algorithm. In degrees and a Q for 0 in degree nodes. DFS is a simpler method. Pushing them into a stack upon finishing their neighbors. Then reversing the stack. I see, I see. Hi, Catherine. Thanks. Hopefully the delay is gone. We'll see if the delay is gone. For each unvisited node in the graph. Okay. I think I get this. Delay is gone. Well, it's also the start of the stream. I think the delay, like, periodically grows. Okay. Recursive helper function. So this is ordered. Visited. Haven't visited anything yet. So we start with, I guess we can start with you. Start with you. For each unvisited node in the graph. I think here it's okay to just start with you because we don't care about nodes that we never see. DFS. Node. And then we're just going to call on you. Mark the current node as visited. Recursively call DFS on all unvisited neighbors. For target in edges mode, DFS target, all unvisited neighbors. Target not visited, not in, visited. Then we recurse. And then order dot append. I guess I could use the deck here. It doesn't really matter. Order dot append. No. DFSU. Print. order. Let's see if this works at least. Whoa, whoa, whoa. That's not right. That's not right. Oh yeah. Why didn't I get edges here? Whoops. Source. That's not right. There we go. And then U all the way down to out. Okay, great. So we have our ordered list. And now we can count the ways. This is paths. Int. Right. I think we just start on the back and go forwards. Right. Yes. For node, oops, in reversed order. Well, I guess, do we have to start with 1? Yes, I think U is 1. Okay. For target hidden targets. So edges node. Paths to target plus equal paths node. I think that's it. And then print paths out. I think that's it. 791. Does that seem reasonable? I should test this. Nah, let's just YOLO. Why won't this go away? There we go. That's right. Hey. Okay. Thanks in part to your analysis, they also figured out a little bit about the issue. They now know that problematic data passes through both DAC and FFT. They're still not sure which specific path is a problem, so they now need your help to find every path from SVR to out. However, the paths you must find must all also visit both DAC and FFT in any order. Every path from server to out. Do I just go from server to DAC to out? Was SVR in here? Doesn't look like it. Only 2 paths visit both DAC and FFT. I mean, don't I just go from server to FFT to DAC to out, and then server to DAC to FFT to out? If possible. It might not be possible. I think. I mean, there are only 700 paths. There aren't that many paths. You could just actually just enumerate all of them, right? Well, I don't know how many there are in this. Well, let's find out. Okay, that was part one. We'll reset ordered, visited, and we'll do DFS on SVR. And then we'll do paths again. Here, we'll make this function. Count paths, source, target. Source. And then return paths to target. Oh, I double use target. Ba 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 ba. Final target. How about that? Okay. This one's from you out. All right. All right, so let's try that again. Okay. VR to out. Holy. Nope, we can't count those. We cannot count those. But I think we can just count how many go to FFT, then DAC, then out, and then how many go to DAC, then FFT, then out. Right? Right? And then multiply. Okay, I'm pretty sure count paths. I can always use the same order, right? I should be able to. Okay. So my theory is server to FFT times FFT to DAC times DAC to out is option one. Plus DAC to FFT to out. Pretty sure that should be right. Okay, this is not hard. I spent a lot of time on the second part, even though I shouldn't have. Like, I don't know. Oh, look. Everybody's done already. This is not a hard problem. Larry finished quickly. Here, let's see how long. I don't know why I was being slow. Um, Wait, I'm looking at the wrong one. God damn. Okay. Uh, I said 6 minutes. Yeah, look. 2 minutes, 2 minutes, 4 minutes. Mostly I was like 7 minutes. Mostly I was like, this is way too easy. What is going on? I lost a lot of time on part one because, wait, that's not even. I'm way down here at 11 minutes. I spent a lot of time on part one. Larry did in 2 minutes. 2 minutes. Um, oh, you know what? I bet Larry used Network X. No, anyway, I spent a lot of time because I had to look up how to do topological sorting. And then I had to read how to do topological sorting. Even though I should just know how to do topological sorting, I don't know. It's not something I've done in a while. Um, okay, so yeah, let's go back over the problems. I have not been very good about going over the problems. Okay, part one is we have a graph. It's a directed graph. Each edge only goes one direction. Um, and it's acyclic. Well, we assume it's acyclic. In general, advent of code, they're not going to throw in a cyclic graph because then the problem doesn't have a solution. Okay. And then you need to figure out the number of paths. Uh, so two things. One, you need to topological sort the nodes, and that simply means that you never go backwards. Um, the list of nodes is such that um, when you process a node, you know that there are no inbound edges to it, and so you don't have to worry about it. Um, so we did a topological sort so that we know that once we start at U and then we go from there that did oh, there's no overlay for that. So you can't tell whether there's a delay or not. There's no audio that like fires from that. I probably saw it like 10 seconds late. So the delay, if there's a delay, it's because I just didn't see it. It didn't make a sound or anything. Twitch wants you to share that? Oh, okay. Okay. I saw that right away though. Twitch wanted me to share that. So you can tell if there's a delay if I responded right away or not. Um oh yeah, so we did no delays. Yay. Great. I figured out what the problem was. Okay, yeah. So we topologically sorted them, and then you need to count the ways through the graph. And the way to do that, and I only know this because I looked it up literally yesterday, um, uh, is with dynamic programming. And basically, you take each node in the topological sorted order. You take each node, uh, you take however many paths lead into it, um, and then you take each edge going out and you add that to each edge going out. That's all we do here. All we do is for given a node in the topological sorted order, you just count uh you just add the number of ways to that node to the next node. And that's it. You do that for all of them, and then um you get the final answer. This algorithm is O of edges. Is that right? Yeah, O of edges. O of V plus E. Vertices plus edges in your graph. Which there's not that many here. There's probably what, like 2,000 or something. Maybe a bit more. No, maybe about 2,000. Certainly less than 3,000. Anyway, not that many. V plus E. So it was very fast. That's why it ran very fast. Um, Same thing with the second part. There are many, many, many paths because they can grow exponentially. But anyway, it's fine. I don't know. There's not really much to say about this problem. This problem's not that interesting. Okay, let's see. Oh wait. First, let's see if the timing finally updated. It did. Ha! Look, I'm still beating Larry, just barely. He started late on 2 days, so it's not really a fair comparison. I finished six. Somebody finished before me. Oh wait, you can't tell from that. Oh, because he finished very close to five and four finished very close together. It just hadn't updated. Anyway, 18 minutes. I'm slow. Whatever. Minutes per star. Yeah, yesterday was hard, huh? Yesterday was hard. Today is easy. Today is textbook. That's the thing. Today's textbook. Um, Let me see. Oh, interesting. Huh. Another textbook. Uh, okay. I can end stream because this is not entertaining. I'm just typing on Discord. Type. Okay. All right, that's it. What do I have to say? Nothing else. All right. Have a good night. So quick today. Yes, today's been. Yesterday was hard. Today was easy. Lots of people have finished already. It's great. I do like that so far. Advent of Code. Each day has been like a different type of problem. Uh, Whereas I feel like with the 25 days, sometimes you get like repeat concepts like caching or recursion with caching, or normally there's some sort of cycle detection. I'm surprised we haven't seen cycle detection yet. Anyway, we haven't seen Dijkstra's either. We haven't seen, I don't know. Anyway, today each so far each day has been like a different core computer science algorithm, and but they've been very textbook, which makes it easy and quick. Okay, that's all. I got nothing else to say. I'm gonna end stream. Thanks for watching. That's all.